All right, bio 30. So we're going to continue our discussion about membrane communication in a neuron by discussing what an action potential is. So we've already danced around this in the last video, and so now we're just going to add some details to it. So when a neuron is excited, it generates what's called an action potential. Okay, this is the movement of potassium and sodium to create a charge difference, which will allow that electrical signal, because remember, neurons are all just electrical signals, to get transmitted down the wire or the neuron. And so we're just going inside of that neuron and we're explaining how that electrical signal is actually transmitted. So first off, the sodium potassium pump, that active transport pump we just talked about in the last video, it's turned off. It doesn't do anything. So the sodium potassium pump only turns on when the membrane is trying to go back to rest. When you're trying to generate an action potential, the last thing you want is to turn it off. So you want to keep the last thing you want is to turn off the action potential. And so the sodium potassium pump doesn't operate when you're trying to run an action potential. So here's a little graph, and we're going to get used to seeing this here. There's four portions of this graph I'm going to explain to you. One is a point we're always going to look. So time is on the bottom of this chart, and on the left we've got membrane potential in millivolts. We start off with negative 70 millivolts, and that's our rest. We then increase to a positive 40 millivolts. That's this number 2 labeled orange. Then we go back down to a negative something, and then we go even below negative 70 before we come back up to that resting negative 70. So these four portions all have terms and names, and we'll describe each in detail. So we've got resting membrane potential, we've got an action potential event occurring, and then it starts over again. So here's a bigger version of this graph. All right, so when we look at this here, we are going to see that at this point we've got resting potential. At this point, we will say that the neuron is polarized. And then up here, we have an action potential where we have now depolarized our neuron. Then we get to a point where we are hyperpolarized. We're even past the negative 70 millivolts, which we called polarized at the beginning. Now we go past that. We're even more negative than negative 70. And then it only stays at that point for a short amount of time and then levels back out to negative 70 millivolts. And then and my face is probably cutting this off here, but this is resting potential, and this is where you get repolarized. So I'll explain all four of these sections to you. All right. So probably one of my favorite ways to look at this is just to label it all on the graph. When I teach this in the classroom, sometimes I ditch the notes and we'll just have a graph out and we'll explain everything using this graph. So if you recall in the last video, we said we're moving sodium, which is normally on the outside, inside, and we're moving potassium, K, which is normally on the inside, because the king is always inside his castle at rest, to the outside. That's what happens during a membrane potential event or an action potential. So when we go from rest and we start to depolarize, or in other words, we start to increase the resting membrane potential in positivity. We started at negative 70, and we're trying to go all the way up to that plus 40 millivolts. In order to do that, the inside has to become more positive. The way we're going to do that is allow the sodium channel to open, and sodium is going to rush inside. So that's going to depolarize our membrane. We're going to get more positive. We're going to go from negative 70 all the way up to the plus 40. Once that's happened, you've got what's called an action potential. We are going to have a depolarized membrane. We've reached the positive 40 millivolts. The signal was propagated through that section of the neuron. And it's going to happen to every section of the neuron until it gets to its destination. So it's not something that happens once. This is something that happens over and over again as the transmission is moved along a neuron. Now, when this portion of the neuron has reached positive 40 millivolts, it needs to go back down to that resting negative 70 because it needs to prepare itself for another transmission to come through it. It's as if you have a road and your car is driving through it, and every time your car drove through it, you created like giant holes in the ground. And so before the next car could come through it, somebody had to come behind you and like repave the road so that the car behind you could drive over it, and then it would create holes in the ground, and then someone would pave over that, and then another car could drive behind you, that car, and then someone would pave holes behind it. So it's like as the nerve transmission, the electrical impulse moves along a neuron, you always have to go back to the resting membrane potential before the next electrical signal can pass through. So then it tries to go back, but then it goes back too far. Instead of going down to negative 70 millivolts, It goes way too far. And so it needs to fix that. So here, when we have our action potential and we've depolarized our membrane, we need to repolarize it. We have to repave the road behind us. And so potassium is now going to rush out of the cell. So remember, K is always inside its castle. Now the potassium is going to rush out so that we can recreate a positive membrane on the out. Sorry, we recreate the positivity on the outside and the negativity on the inside at rest. So potassium rushes out, and then the sodium potassium pump is going to kick in near the end of that in order to move the proper amounts, so 3 sodiums back out and 2 sodiums back in, so that the outside can be relatively positive compared to the inside, and we can have that negative 70 millivolt resting membrane potential occur. Now, there's something called this threshold. So the threshold is at negative 55 millivolts. So now I'll just get the discussion of the threshold out of the way right now. It's as simple as you will not have a membrane potential or an action potential occur unless you have a minimum reduction in your resting of your polarization of your resting membrane potential to negative 55 millivolts. So let's say you have a stimulus and it only budged you from negative 70 to negative 60. That's not enough. The threshold, the minimum amount that you have to have in order for a signal to get propagated and for this entire depolarization and repolarization event to occur is negative 55 millivolts. So unless a stimulus is strong enough to change the membrane potential from negative 70 to at least negative 55, the membrane potential won't happen. The action potential won't happen. Now, if it hits negative 55, it's going to happen for sure. So this is what we call an all or nothing response, basically. It's going to hit the negative 55 and go, or it's not going to hit the negative 55 and it's not going to go. And the signal won't get propagated. We're going to come back to this repeatedly. Okay, so here's another, just same picture as we just had, just some notes around it. So now near the end here, when you have finally pumped the sodium back out and the potassium back in using the sodium potassium pump, which was active transport, required ATP, you then have your membrane potential become what's called hyperpolarized. And when it's hyperpolarized, it needs to go back to that negative 70 millivolts. It's just pushed things a little too far. The inside just became a little too negative. And this happens every time. It's a little sloppy when it cleans it up. And so it cleans up a little too much and the inside becomes a little too negative. And so there's a period of time where the finishing touches have to be made to get the ions in the right position so that it can stay at the negative 70 when it can become officially repolarized, or in other words, be back at this point over here at rest so it can start all over again. So that time it takes to clean up the sloppiness to go from this hyperpolarized state, could have been negative 75, could have been negative 80 millivolts, back to the proper negative 70, it's called the refractory period. And this is the time it takes for a neuron to recover before another action potential can occur. So that's going to happen the entire time between the depolarization has occurred and the time that repolarization has happened so that you can start all over again. This is the refractory period. It's the resting period. Okay, so the all or none response, like we talked about, threshold level is a minimum level of a stimulus required to produce a response. And so it has to reach that negative 55. If it just barely budges it, maybe it's negative 60, maybe it's negative 65. That change in memory potential wasn't enough. The signal wasn't strong enough for an actual action potential to occur, so the signal never got propagated down the signal. Now that's important when you think about it. Imagine if every single stimulus you ever interacted with constantly fired an action potential. You would be receiving information from sensors and sensory neurons from everything. But we don't. Our action potentials only occur for stimuli that are strong enough. Now, of course, that could be a subtle touch, for sure. It could be just a hair on your face that's just gently kind of itching you, but it's enough of a signal that it's triggered that action potential. That's why you don't feel like a mosquito landing on your arm necessarily unless it's already bit you, because it's so light the way it lands that it hasn't triggered the sensory neurons in your skin, in your arm, to tell you, oh crap, there's a mosquito on me, because that signal never reached the negative 55 minimum threshold required. That's why we don't hear lots of sounds as well. So negative 55 millivolts is that minimum threshold potential. and it's an all-in-one response. So once it hits negative 55, the whole action potential happens. If it doesn't hit negative 55, the action potential does not happen. So the intensity and the speed of nerve transmission are all going to remain the same. It's just you either have it happen or you don't have it happen. You either reach the negative 55 or you don't reach the negative 55. Okay, so then just to finish off this video, the number of neurons that are excited are going to dictate how intense a reaction is. So if you have more neurons stimulated, you're going to realize that the stimulation is more intense than if you have fewer neurons stimulated. Okay, so we're going to start the next video basically just reiterating an action potential and discussing like how the movement of sodium potassium once again creates this action potential.